So look at these two equations. These are both going to be equations that give us roses. This k, this constant that's in front of sine and cosine, do the same thing. It's going to change the length of our petal. So again, these roses are actually going to have petals, and they might look more like a different kind of flower, but it's the length of the petal, and you'll see kind of what those do. What about this n that's inside of sine and cosine? Well, it does two different things depending on the number. If n is odd, then we have n number of petals. Well, what if n is even? Then it's going to actually double the number of petals. So if we had a 1 in there, we would have 1 petal. If there was a 2 in there, it would be 4 petals. If it was 3, 3 petals. If it was 4, we would have 8 petals. And again, this would be something where we would kind of have a discovery lesson on this. So what if we change sine and cosine? Well, if we change from cosine to sine, it ends up starting off of the x-axis. So let's go over some steps on how to graph a rose. So the first thing it's going to be always helpful is to have the length of the rose, of the petal. It's going to be the first thing that you want to do. We're going to then figure out the number of petals that we need. Again, if n is odd, then n petals. If n is even, then 2 times the petals. We're going to need to find our starting point. If it's cosine, we start on the x-axis. If it's sine, what we actually want to do is start at 90 divided by n. So that n is going to be different. If it was 2, it would start at 45. If it was 3, we would end up starting at 30, and so on and so forth. And kind of like our sine and cosine graphs, when we did all that, we need kind of increments. Well, our increments are going to be based on a full circle divided by how many petals we have. So we're going to do 360 divided by the number of petals. And again, depending on if n is even or odd, changes that number of petals. It's not always going to be n. So looking at this first problem here, we have a 3 as our constant in front of sine. So that means the length of my petal is going to be 3. It's going to be nice to write this stuff down, one, to kind of show work, and also just to be practicing what information we're going to have. So what are the number of petals that I'm going to have? Well, we have an even number inside with theta, and it's 2, so we're going to multiply that by 2 and get 4 number of petals. Where are we going to start? Well, since this is a sine, we're going to start at 90 divided by 4 or 2. Well, our rules say we're going to divide it by n. So n is actually 2. So we're going to start at 45 degrees. And then we need to figure out where our increments are. So we're going to take 360 and divide it by how many petals we have, which is 4. So that means all of our petals are going to start at 45 degrees and go of increments of 90. So 45 degrees is about here, 1, 2, 3, 4 of a radius, and in my increments of 90, just go all the way around in that circle. And what ends up happening with these roses is that they also go through what used to be called the origin. This point now is going to be called the pole. So let's look at what happens when I start graphing this and making it look like a flower or rose. So you ended up getting something like this. And for the explore kind of lesson part of this, you can actually be using a calculator to kind of see, what your flower kind of looks like, but you are going to need to do this without a calculator. All right, so let's look at this next one and let's figure out the information that we have. So the length of our petals are 4 because of that constant. How many petals do we have? Well, since n is odd, n is the number of petals, so 5. Where are we going to start? Well, we're going to start at 0 degrees on the x-axis because this is a cosine graph. Cosine graphs always start at 0. Then, what are our increments? Well, n is odd, and so it's the same number as a petal, so we're going to divide it by 5 and end up getting 72 degrees. So we're going to have a length of 4, 2, 3, 4 on the 0, and then we're going to go by 72. So we're going to kind of go all the way around and put our points. So just try to approximate where 72 degrees is, and then you just start drawing your petals. And there's your rose. So I know they more look like flowers instead of roses, but we just like to call them roses to keep things simple. They don't always have to look perfect, but they should kind of look rounded. Don't try to, connect them with a straight line or anything like that. So the more practice, the better. But as you can tell, like I've been drawing these for a while now, and it just need to get back into the hang of drawing it well.
So this next thing that we're going to talk about is when we're subtracting or adding something on the inside of the trig function. Well, if you remember back to transformations of functions, when we are adding or subtracting things to the input, it shifts our graph left and right. But how do we shift left and right in polar? Well, we don't. What we end up doing is that we rotate it. And to be more specific, we rotate the center of our polar graph. So if I'm going to be doing theta minus d, that's almost like x minus c that we had in function transformations. So in x minus c, we would have a shift to the right in the positive direction. Well, right in the positive direction on the polar plane is going in the positive angle measure, which is going to be counterclockwise. Or if I subtract a negative d or go a negative angle measure, which is going to end up being plus d, we're going to go in the negative angle direction, which is in a clockwise rotation. So just make sure you understand that. So these are examples of those rotations. So let's first think about what r equals 6 cosine theta is. Well, r equals 6 theta, or 6 times cosine theta is a single petal rose. It has a diameter of 6. So 1, 2, 3, 4, 5, 6. So I'm going to go there, and I'm going to draw a circle. I'm going to make that so that it looks exactly like it's supposed to. And then if you want to think about the center of this, it's here. So just understand a few facts about this. If you were to convert this into a rectangular equation, you would end up getting a circle of radius 3 with the center at 0, 3. So that's what's going on here. The diameter of this circle is 6, the radius of it is 3, and the center is not at the center of the pole. So if you were to take that, so I'm going to kind of cheat a little bit and kind of show y'all what I can do here. Hopefully this works out the way that I want it to. So what happens is if I am subtracting pi over 4 on the inside, it's going to rotate this 45 degrees or pi over 4 in the counterclockwise rotation, which I don't remember where the rotation, oh, there it is. I'm going to rotate it and kind of move it around. That's not quite 45 degrees. So it ends up looking something like that. Just going to rotate it a little bit more. If it works for me. Okay. Not quite. There it goes. Probably not the best thing, but what I wanted to kind of show y'all in that video is, in this video, is that it rotated 45 degrees in the counterclockwise rotation. So if I were to do that over here, let's see if I can do this a little bit better on this one. I'm going to rotate it 45 degrees in this direction. Still not quite there yet. And make sure that it looks something like that. And it's a little bit better than what I did last time, but I rotated that 45 degrees in the clockwise rotation because we had plus pi over 4 on the inside of our trig function. So just remember that when you are rotating these, you're rotating the center of the graph.
All right. What about number 6 here? Secant. Well, let's actually figure out what I could do here. Well, I can change this to rectangular. So secant is the same thing as cosine multiplied by cosine. And we end up getting that x equals 3. Well, which one do you recognize easier that it's a vertical line? Well, of course, x equals 3. So do a little bit of converting that we've talked about and get it to be x equals 3. So it's a vertical line on the circle of radius 3 that needs to be completely tangent to that circle. So there it goes, the tangent line x equals 3 to that circle with radius 3. Well, how is that different than the next question here? Well, the only difference is that it's now minus 45 degrees. So maybe recognizing that 3 secant is a vertical line, and then what we're going to do is we're going to rotate that counterclockwise 45 degrees. So that point on the circle 3 gets rotated to 45 degrees, and then we need to make sure that it's completely tangent to the circle, which means that it should only hit that circle at one point. All right, so what about this next one? Well, we have a petal length of 2, but we only have one petal because there's a 1 in front of that theta. Well, if we're starting at 90 degrees divided by n, since it's sine, we're actually going to start here at 90 degrees because 90 degrees divided by 1 is 90. So I end up having a 1 petal length of 2 on the y-axis. So you can think is that if n is 1, then if it's cosine, you start on the x-axis. If it's sine, you start on the y-axis. What if we put some absolute values in front of it? Well, you can kind of think about if I ask you that if the absolute value of x equals 2, then you could say that, oh, well, x could be 2 or negative 2. So I'm going to do the same thing here. In order to take away these absolute values, I'm going to put a plus or minus in front of that trig function. Well, we just talked about what happens if I have a positive petal length of 2. Just looks like this on sine. Well, what happens if I have a negative petal length? Well, it ends up going down here. So we almost have like an infinity symbol or like a 2 petal rose, but it's only on that x-axis, on that y-axis. So if it's cosine, it will change it to be on the x-axis. What about this last one? Well, what I could do is I could convert it to rectangular, but it's going to be more challenging. What I could honestly do is factor out an r, and if I set each of those equal to 0, I get r equals 0 and r equals 2. Well, I know what r equals 2 looks like. That's a circle of radius 2, so I just try to trace the circle of 2. A little bit better job than the first time. But what is r equals 1? What would that circle of radius 0 be? Well, it would be what used to be called the origin, which in polar is called the pole. So one special formula is when we have r squared equals something like that looks like this. It's always 2 theta. Everything's the same. The only difference will be is what this coefficient is. So anytime you have an equation that's r squared equals something cosine or sine 2 theta, it's called a limniscate. It is going to be important for you to know the vocabulary words, so make sure that you're practicing these words. So let's see how we graph this. So notice on this first one, again, we have r squared, we have a perfect square, and we have cosine 2 theta. And again, it's always cosine 2 theta. So a squared, in this case, is 9. So that means a is 3. So a is going to be this length of our petal. So since this is cosine, we're going to actually draw this on the x-axis. And if you think about it, 2 theta, we have 2 petals, but since it's a limniscate, since it's r squared, what we only end up having is 2 petals. So what we're going to have is a petal of length 3, and it almost looks like an infinity symbol. So if you were to graph this on a graphing calculator and have it like trace out what it's actually doing, you'll notice that we end up having 4 petals is just overlapped. So here there's 2 petals on top of each other. Over here there's 2 petals on top of each other. Just some information to know, but that's what a limescate looks like. We square root that coefficient, and that's how long my petal is. So for this next one, we have that a squared equals 25. So that means our length of the petal is going to be 5. But since this is sine, we're going to start off of the x-axis, but where do we start? Well, it's the same process that we do for roses. We're going to start at 90 divided by n, which in this case is 2. So we're going to start this at 45 degrees. So 1, 2, 3, 4, 5 is the length of my petal. And again, I'm going to go 1, 2, 3, 4, 5 in both directions and have kind of like an infinity symbol. So something that I always like to bring up here is that this is actually $1 million answer. What do I mean? Well, on Who Wants to Be a Millionaire, this was actually the $1 million question: is what graph in math do we have that looks like an infinity symbol? And the answer was a limescape. All right, so the other graphs that we're going to be talking about are called limacons. So limacons, you can tell the difference between limescapes and this is that we have an addition and subtraction. So you can kind of see that I did a little bit of prep work here and drew my axes. And I'm going to explain what each one of these graphs are and how we draw them out. But make sure that you understand what's going on here and how to recognize them and the information that we need in order to graph them. So for our first case here, we're going to say that A equals B. Well, anytime that these two numbers are exactly the same in our equation, it's called a cardioid. So we kind of saw a little bit of this on the other notes where we put it in the calculator and graphed it. It's a cardioid. It almost looks like a heart. So there's some information that we need to know. The first thing is, where is the major axis? So you can kind of see that I try to draw it as uniform as I can. And you can see that I gave myself some little tick marks so that they can be safe or the same and to scale. But we need to figure out a major axis. And I'm going to probably abbreviate this along the way. But since this is cosine, cosine's x, so that's going to be the x-axis. So that's how we're going to know if it's the x or the y. If it's sine, it's going to be the y-axis. But we need to know which part. Is it going to be the positive part or the negative part? And that's where the plus and minus come into play. So if it's plus, we're going to start, or the major axis is going to be on the positive x-axis. So what do I mean by the major axis is that that's where the majority of my graph is going to be. So the majority of my graph is going to be on the positive x-axis side. So let's figure out how we graph this. Well, this a value here, and you can see in this general equation, a is the number that's being added or subtracted to sine or cosine. That's going to be my minor axis. So this 3 here is going to tell me to go up and down or on the opposite axis of the major axis. If the major axis is this, the minor axis is here. So this 3 here, this a value, is how much I'm going up and down. So I can say that this is a and a. Well, if we add them together, 3 plus 3, we end up getting 6. That's how much length I'm going to go on the major axis. So 1, 2, 3, 4, 5, 6. So this is a plus b. So I'm going to have a point here at 3, a point here at 3, and a point here at 6. Well, with cardioids, what we're going to do is we're going to end up crossing at the pole as well. And you have to be very careful when you graph these. These are kind of elliptical, so make sure that you're drawing them like circular. So this is what your cardioid looks like. So don't make it look like a heart where it kind of comes to a point. It should be elliptical. It should be curved. So make sure that you're kind of giving yourself that kind of wide area there. Okay, so again, this is brand new stuff. So we're going to learn how to do these graphs well with practice. So you can kind of see my graph here that I did some prep work out off camera. can see that, oh, well, look, I have a lot more tick marks on this negative y-axis. How do I know that's the major axis? Well, again, the major axis depends on what operation we're doing. If it's adding, it's positive. It's subtracting, it's negative. And if we're dealing with sine, we're going to talk about the y-axis. Okay, so my major axis, the majority of my graph is going to be on that negative y-axis. Well, you can kind of see by my tick marks, well, how did I get all these? Well, it's going to be that a plus b length. So 4 plus 6 is going to be 10. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to have a dot there. My minor axis, the length that I go from the kind of pole, the center outwards, is this a value here. So I'm going to go 1, 2, 3, 4 and have a dot. And then 1, 2, 3, 4 and have another dot. Well, this is not going to be a cardioid. This is not going to be a cardioid because this a value is less than b. So what I'm going to have to do to figure out what's going to happen here is I'm going to have to subtract a and b. And I'm going to get a different length. Well, what happens if I subtract 4 and 6? We end up getting -2. Well, what if I would have done that over here on this one? What if I did a minus b and did 3 minus 3? A minus b is 3 minus 3, it's 0. So you can see that that's how my graph kind of starts here at the pole and goes out that way. Well, -2, well, you kind of think about it like, okay, well, if I were going to plop 2 points this way in that direction, it would have been +2. If I'm going to do -2, what I'm actually going to do is plot that point inside that major axis, and I'm going to still go through the pole. This is going to be called a limacon with an inner loop. And I'll graph it here to see what it looks like. So again, this is something that you need to be practicing, that if a is less than b, you need to realize that it's a limacon with an inner loop, because if I do that subtraction of a minus b, it goes inside that major axis and we end up having an inner loop. So this is what that limacon looks like. So then there's going to be another limacon that we're going to have here, and it's when this value of a is between one value of b but less than twice of it. So 6 is bigger than 4 but less than 8. Okay, so that's what's going on here. So 6 is bigger than 4 but less than 8. If we have a situation like that, this is called a dimpled limacon. Why is it going to be dimpled? Well, let's look at the graph. So let's figure out our major axis. Our major axis, it's plus, so it's positive. And we're dealing with sine, so we're dealing with the y-axis. So you can kind of see that's where the majority of that picture is. That major axis is always a plus b. So if I add 6 plus 4, I end up getting 10. So 3, 4, 5, 6, 7, 8, 9, 10. My minor axis is that value of a, which is going to be 6. So 1, 2, 3, 4, 5, 6, and plot a point. And then 1, 2, 3, 4, 5, 6, and plot a point. So what about this a minus b that we did and introduced in part B? Well, a minus b in this case is going to be 6 minus 4, which ends up being a +2. So since it was -2 for that inner loop, we went into the major axis. Well, since this is +2, we're actually going to go away from the major axis, like that a plus b part, and plot a point there. So again, the way that I'm getting these values is that this minor axis from the pole has a value of a. This longer part, that major axis, is going to be a plus b. And then this piece here is a minus b. If a minus b is negative, it goes this direction and becomes an inner loop. So again, it takes some practice, but you can see how this kind of part where here is dimpled. It kind of has like a little indentation, um, caving in a little bit. So these are called dimpled limosons. Now, this one does not go through the pole. You don't have like a loop going here. We had the pole here, since we had a minus b is 0. We had a pole here because of it having an inner loop. Since it was dimpled, it doesn't go through the pole for this one. So now, what if this a value is greater than or equal to twice the b value? So in this case, 5 is greater than 2 times 2. It's greater than 4. So this is what we call a convex limoson. Okay. And again, make sure that you're practicing the vocabulary and being able to recognize which one is which. So let's figure out all our information. So the major axis is going to be the negative x-axis because we have subtracting cosine. So that means the majority of my graph is going to be here. So that length is going to be a plus b. So that's going to be 7. 1, 2, 3, 4, 5, 6, 7. My minor axis is that a value. So 5. 1, 2, 3, 4, 5. And then the other way as well. 2, 3, 4, 5. And then my value of a minus b, well, that's going to be 5 minus 2, which is 3. So I'm going to go 3 in that opposite direction of that longer major axis there. And then we connect the dots. So it looks a lot more elliptical than it did. So how are you supposed to tell the difference if you're supposed to dip into and make it a dimple versus making it look convex, which means that it's popping outwards? Well, you need to know the relationship between A and 2B. So is A, bigger than B but less than 2 times B, or is A greater than twice B? You need to make sure you're able to distinguish those two. All right, so we did a lot of converting from conic sections to polar equations and vice versa, but sometimes it's going to be easier to recognize certain things to know what the graph is going to look like. So what we're going to have is some facts here. So 5 plus 3 here, well, 5 is less than twice b, but greater than 1 of b. So this one here is a dimpled limoson. If I take that dimpled limoson and I put it in a denominator of a coefficient of just any number, whatever number this is, if you put a dimpled limoson in the denominator, we end up getting an ellipse for our graph. Now, dimpled limosons and convex limosons are kind of the same. They just look a little different. So we're going to add, if it's convex as well, it also gives us an ellipse. For number 2 here, A is less than 5. So this is going to be a limoson with an inner loop. It is very important that that whole sentence is put together. It's a limoson with an inner loop. If you just say it's an inner loop, what is an inner loop? We don't know what it is. It's a limoson. It's a very specific graph with a inner loop since A is less than B. Well, anytime you have this, you end up having a hyperbola as your graph. And some of y'all are going to be like, well, why? Well, we're going to actually explore that here in a bit. Well, what happens when A and B are the same? Well, this is a cardioid. You can be a little bit more specific and say it's a cardioid limoson, but cardioids are limosons, so you don't have to worry about being specific. If you have a cardioid in the denominator of a fraction, you end up having a parabola. So let's talk about how we can graph these types of problems. All right, so there are 3 parts to this next question. We need to name the conic, determine the direction, and plug in our quadrantal points. And if you don't remember quadrantals, I try to get y'all to remember that from like the first 6 weeks. These are the angles that are on our axes. So we're going to talk about 0, 90, 180, and 270. So naming the conic is going to be some helpful information if you're given quiz questions and not asked a graph, and you don't have to go through all that. If you recognize that, hey, down here, A and B are the same, so this is a cardioid, the cardioid in the denominator ends up giving us a parabola. Well, determine the direction. What I'm going to do is I'm going to help y'all kind of graph it first and then see what happens to that and show the direction that it's going. All right. So here's a table. Here are our 4 quadrantals, 0, 90, 180, 270. Again, the angle measures that are on our axis. So now what we're going to do is we're going to plug in each one of these into that equation and simplify it. Well, cosine at 0 degrees is 1. Well, then if you do 3 times 1 plus 3, you end up getting 6, and 6 reduces to 1/3. If you plug in 90, cosine of 90 degrees is 0, times 3 would be 0, plus 3 would be 3, so you end up getting 2/3. This is why we use the quadrantals, because we're going to get answers that are 0, 1, or -1. If we plug in 180, cosine of 180 is -1, times 3 is -3, plus 3 is 0. So you end up getting 2 over 0, which is undefined. If you plug in 270, then cosine of 270 is 0, times 3 is 0, plus 3, and then you end up getting 2/3. So we have thetas that are, those quadrantals, so 0, 90, 180, 270. And then we have our radii. So what I did is I provided tick marks here that, I'm not going to call these 1 and 1/3 and whatever, 1/3 or 2/3. I'm going to actually say that this is 1, 1, -1, and -1. So if I'm talking about the point 0 degrees 1/3 radius, then, you go 1/3 about there. There's my point. At 90 degrees 2/3, well, 90 degrees is up here, 2/3 maybe somewhere here. 180 is undefined. There's no point going to be here on the 180 degree thing. And then 270 is about 2/3, so we have that. And then we connect our dots and get a parabola. So this is how a cardioid ends up giving us a conic section that is a parabola. So if we're determining the direction here, well, this is a parabola that's opening left. So then this is going to be what we call a horizontal parabola. Okay, should be an O, not an A, but it's a horizontal parabola. If it was going up and down, then it would be, or up or down, it would be a vertical parabola. A good way to recognize this is that, well, it's dealing with cosine, so the major axis is going to be that horizontal, so that's how our parabola is going to be opening. All right, so in this next one, since we have that our A is actually equal to twice our B, this is a convex limacon. But either way, if it's dimpled or convex, it's going to give us an ellipse. So ellipses are almost circles, but longer on one side. Well, kind of like what we figured out on the last one, since it was cosine, the major axis is horizontal, we got a horizontal parabola. Since we're talking about sine here, our major axis is that y-axis, so this is going to be a vertical ellipse. Okay, so just make sure that you're practicing that. Again, you could plug in the quadrantals, get our values, and end up doing that. So again, figure out your unit circle values. Sine at 0 is 0. So if we plug in 0 there, we end up getting 5/2. Sine at 90 is actually 1. So if we do that, we end up getting 5. Sine at 180 is 0 again. So we end up getting 5/2. And then if we plug in 270, sine at 270 is -1. We do all the math, we end up getting 5/3. So let's plot those points. So there are the points, and then we connect our dots. And there's our ellipse. So again, just remember that when you're plotting these quadrantals, 0 degrees, 5/2, 95, 180, 5/2, and then 270, 5/3. All right, so for this next one, we have where A is less than B. So this is a limacon with an inner loop. Limacons with inner loops ends up giving us hyperbolas. And since this is, cosine, major axis is the x-axis, it's going to be a horizontal hyperbola. All right, so let's plug in our quadrantals. So we end up getting 2/5, 1, -2, and 1. So if I'm going to plot 0, 2/5, somewhere here, 91, 180, -2. How do we plot negative radii? Well, if it was +2, it'd be here. But if it's -2, I actually go in the opposite direction and I plot a point here. And then 270 has a radius of 1. So then we connect our dots. Well, those are easy to connect, those three here. But what about this point that's way over here? Well, remember that hyperbolas are kind of like those two parabolas that are on the same graph. So your other one goes in the opposite direction, like this. Probably could have gone a little bit further down, but just a sketch of a hyperbola. Okay, so again, limacons with inner loops gives us hyperbolas. What about this last one? Well, it's not a limacon because it's not like an a plus b cosine or sine. It's 5 cosine and 2 sine and added together. So it's not one of these three, but I can still maybe convert this to rectangular. If I multiply by the denominator and distribute the r, we end up getting 5r cosine plus 2r sine equals 3. Well, r cosine is x. R sine is y. So what do we have here? It's a line. This is in standard form. I believe the easiest way to do standard form equations is to do the cover-up method to find the x and y intercepts. If you plug in 0 for y or cover up y, you can find out that the x-intercept is 3/5. So 3/5 is somewhere maybe here. If you cover up the x, you're left with y. You end up finding your y-intercept is 3/2. So how many points do you need to draw a line? 2. And that's all you need to do.